Okay, so here we try to derive the electric potential due to a charged particle. So by making use of the definition just mentioned, so here it says the electric potential difference between 2 points I and F is Vf minus Vi equals negative integration of E dot ds. So this is just the definition, and we consider for a radial path, and we try to pick. Try to pick Vi is at R. This is the I point. This is the F point. F point is from infinitely far away. Okay, so which means that we try to move this charge from R. Okay, so according to this, we try to calculate the potential due to a charged particle, which is this one. So the axis is starting from this point. The R axis is actually starting from this point all the way upward. This is the R axis. This is This is 0. R equals 0. Okay. And then here is R equals to small r. Okay, and then we try to or actually capital R I should be. Or maybe small r is okay, and then we try to move it to infinite far away. So here we have a setting like this, and and according to chapter 22, we have the E field. Which is K times Q over R squared. R squared. Then we can put this thing into here. Here we also try to let Vf will be 0 at infinitely far away, and then Vi will be the V we would like to compute. Okay, so which means that we try to here we have a potential, and then we try to move it away to infinitely far away. So the potential change will be 0 minus this potential at this point. So it will be the same if you try to have a charge infinitely far away and then move it to that point. But this way will be easier to handle. Okay, if we have the negative side will be easier to handle. If you try to move it from infinitely far away to this point, it will be very easy to make mistake for the integration. You will possibly have an additional negative sign. But if you are careful enough, then you can still get the same result. Of course, if you are interested in the mathematics, you can try it at your home. But I try to work on this version. Okay, suppose we have these two assumptions, we can just put it to here so that it makes it like 0 minus V equals to the integration. And then we try to plug in this E into there so that K and Q are constant, so that we can put it outside, and then R squared is related to the integration. So in such a way we have integration dr over r squared. We try to make it capital R because if you make it a small r, this one is also small r, then these two this r and that w variable will be the same. So we try to make it capital R at the very beginning, and then finally, after getting the result, we try to replace this capital R by small r. So here we have capital R here, and this integration is easy to calculate for a polynomial. So this is actually integration of dr, r to the -2 dr, okay, from r to infinity. So it will be 1 over r, and then with a negative sign, evaluate from r to infinitely far away. Okay, so evaluate from r to infinitely far away, it will be negative 1 over infinity will be 0, and then minus negative 1 over capital R. So it will be 1 over R. So it will be 1 over R, and then finally, so it will be Q over 4 pi epsilon naught, and then times 1 over capital R. And then finally, we switch R back to small r. So finally, we have V equals K times Q over R. K equals Q over R. So this is the potential generated by a charged particle. Okay, it is related to this K, this K, and then the charge, and also the distance. Okay, so here if we have a group of charged particles, which means more than one, then we can try to compute the potential one by one and then add them together. And this time the potential is a scalar, so in that case we don't need to do the vector sum. We don't need to decompose all the vectors into x, y components and then add the components together. Here it's just a scalar, so we can just add all the scalars together. Okay, here is you should have a k here. We should have a k. Okay, so so here it mentioned that the potential is the algebraic sum of the individual potential with no consideration of directions. Okay, so here we have a highlight. It says a positively charged particle produces a positive electric potential, and a negatively charged particle produces a negative electric potential. So, yeah, so it is very straightforward. Okay, so here we have a track point to see if you have understand the difference between scalar and vector field. So here it says, the figure here shows three arrangement of two protons. Okay, sorry, two protons. 就两个质子啊，两个质子都带着正电荷，正一的电荷。And then the rank the arrangement according to the net potential, net electric potential produced at point P. Okay, by the proton, greatest first. Okay, for part A, point P is here, and then a proton with a distance small d, and then another proton with a distance capital D. Okay, so these two are on the right side. Okay, and then for the part B, okay, one is here, one is here, one is at the bottom, one is on the left side. And then for the part C, one is on the left, one is on the right. Okay, it asks you for the potential at point P for these three cases. Which one is the greatest? Which one is the greatest? 哪一个最大 ？A、B、C， 谁最大 ？Electric potential。之前教的年份通常都会打错的，通常都打错。 A、B、C 哪一个最大？觉得哪一个最大？啊？想一下，有没有想到的？应该很简单的，没有什么好算的。哪一个最大？就这个公式算呢，就是你要算的话，就是这里啊，现在有2个嘛，哪一个最大？没有答案吗 ？A 吗？恭喜你，你又再答错了。维持着这个良好的传统，都是答错的。所以是3个都一样大的。3个都一样大。为什么啊？为什么啊？你算一下嘛，这个的话是 k 乘以1除以 d 加上 k 乘以1除以大 D 啊。第2个也是 v 等于 k 乘以1除以大 D 加上 k 乘以1除以大 D。然后第3个也是一样啊 ，v 等于k 乘以1除以小 d 啊。加上 k 乘以1除以大 D 3个都一样，因为它是 scalar 嘛，所以跟方向无关，所以是 same potential at A, B, C。如果是问 E field 的话，就是 A 最大。A 最大 ，B 第2 ，C 第3。但是如果是 potential 的话，就是一样大。这个好像我教那么多年，好像没有人答对。OK， 所以就是要注意的话，就是 potential 就是存量啊，存量场。那它们加总的话，就是数字加起来。所以算这个 potential 蛮简单的。如果是这个比如说是几个粒子的话，那你几个数字带进去之后，直接加起来就好。那你不用再算什么分量。就比如说像第21、22这样，比如说算力的和有几个例子，比如说有一个 sample problems， 有一个 selected problem 是几个例子算几个电荷算总的力，或者是算总的电场，那你就算那些分量，那就很麻烦，这个不用。Okay, so here we have a sample problem. So it says what is the electric potential at point P located at the center of a square of point charges? The distance D is 1.3 meter. Okay, this is a square, and the charge are Q1, Q2, Q3, and Q4. Okay, so actually we need to know the distance R. Okay, distance R. Okay, so this will be a right angle, and then this one and this one will be the same. This will be 45 degree, this will be 45 degree, and in such a way we will have R equals D over square root of 2. Okay, so here we would like to calculate the potential, the potential at point P due to the 4 charges. So V will be sigma Vk, k from 1 to 4. Okay, so it will be equal to K times Q1 over R, and then plus Q2 over R, plus Q3 over R, plus Q4 over R. Okay, so so it would be nothing but K times square root of 2 over D. Okay, so we just try to factor this out, and then we have Q1 plus Q2 plus Q3 plus Q4, and then we can put in the number. So this is 8.99 times 10 to the 9th power, square root of 2 over. Okay, this is 1.3. And then for here, nano is 10 to the negative 9 power. So we have 12 minus 24 plus 31 minus plus 17 times 10 to negative 9. Okay, so it will be 350 volts. Okay, at this point. Okay, actually, this figure also draw the equipotential line here, but actually it's not easy to plot it out by yourself. You need to use a computer program to compute all the potential over the space, and then you try to connect all the potential of 350 volt together to get this curve. But the simple idea is that this one is positive, this one is positive, this one is also positive, this is negative. So this equipotential line somehow separate the positive and negative charge into two groups. Yeah. Okay. Yeah. Okay, so here we have another sample problem. Here it says 12 electrons are equally spaced and fixed around a circle of radius capital R. Okay, capital R. Relative to V equals 0 at infinity, what are the electric potential at E field and E field at center C of the circle due to these electrons? Okay, so for question A, the V should be K times, all of them are electrons with negative E over capital R, and then times 12, okay, because we altogether have 12 electrons. Okay, so it will be negative K 12 KE over capital R. So this is the potential at the point C. But the E field will be a zero. Because, for example, this one and this one, the opposite side of the two electrons, they will generate E field cancel each other. So all the 12 electrons will generate E field that are all cancelled at point C. Okay, so the question B, it asks you if the electrons are moved along the circle until they are non-uniformly spaced over a 120 degree arc， 就是在这个120度的弧上面随意的分布。What then is the potential at C? How does the electric field at C change? Okay, so here we wouldn't change. Because it's only related to the charge amount and also the distance. The distance doesn't change, the charge amount doesn't change. So the V doesn't change either. So negative 12 KE over capital R at point C. But here E isn't 0. E is not equal to 0. Yeah, we are not able to compute the E field, because it is just randomly allocated at the arc. What we can say is that E is not 0 at this case. Okay, so this one is quite simple. Okay, so next one, we will talk about the potential due to a electric dipole. Electric dipole 就是在22章的时候，我们有介绍过这个电偶electric dipole。那这一次的话，我们来算这个 potential。那这个 potential 是蛮有趣的啊。我们设计天线的时候，其实会把这个式子来用。Okay, so here it says the net potential at P is given by V equals V plus V minus. Okay, so we only have two charges with the same magnitude but opposite sign, and then they are placed close together with a small distance d. Okay, so here we can try to compute the potential at point P. Okay, if you still remember when we try to compute the E field generated by the dipole in chapter 22, we can only calculate the E field along this z-axis. Okay, all the other positions we don't have a closed form solution. But here, as much as the potential is easy to calculate, we can actually calculate the potential generated by this dipole. Okay, so here what we need to assume is that the distance is far away. The distance is far away. Okay, so so it says we can approximate the two lines P as being parallel and their length differences being the length of the right angle hypotenuse. 就是假设说这个 P 点很远，这个 P 点很远的话，那这一根绿色线跟这一根绿色线，你就可以把它视为是平衡的啊。需要这一个 P 点很远，这个 P 点很远，那这个过来的话，它才会是平衡的啊。那我们需要用到的是这个 R plus 跟 R minus 的差。那假如说这个 P 点在这里，这个 P 点也在这里，你说为什么这么奇怪？只是这么奇怪。那这个 R plus 跟 R minus 的差就是这一段就是这一段。就是假设说这个 P 点很远这个 P 点很远。Okay, so here we can have V minus V plus will be d cosine theta. D cosine theta. Okay, so the theta will be the angle between the point connecting to the middle point, and then here is this one is the theta. And if you assume P is infinitely far away, in that case, this line, and this line, these three lines are parallel to each other. So in that way, this is theta, this is also theta. Okay, so we assume this P is far away, or we can call it a far field, 远长。Okay, so and also we can assume that R plus R minus is equal to R squared. R squared is this one. Okay, R squared is this one. if P is very far away, then we can assume that R plus is similar to R. R minus is also similar to R. So R squared will be R plus R minus. Okay, so by having the far field assumption, we can have these two assumptions. Due to far field assumption. Okay, so in such a way we can approximate V plus V minus like this. Okay, so going back to here, we have K times Q over R and plus another Q over that R. And then we can have R plus R minus here, and then R minus R plus in the numerator. And then Q, again, we can put it in the front. Okay, so we can put this assumption to here, and then also put in this assumption to here. So that we have a QK, this is QK. And then d cosine theta is here, is d cosine theta. And then R squared going to here. Okay, and if you still remember, P is QD for the electric dipole moment. So we can actually correlate these two QD to be this P. And finally, it turns out to be K times P cosine of theta over R squared. OK， 所以这个就是跟这个天线的设计有关啊，天线的设计有关，什么意思？就是说，那种最简单的天线，你可以把它视为一个dipole，那它接收信号的时候，它就跟这个角度有关，这个角度有关。所以如果这个角度是0或者是180度的时候，这个 cosine theta 就是正1负1的话，那整个 potential 就会正负最大。但是如果 theta 是0度的话，不是 theta 是90度的话 ，cosine theta 会是0，它 potential 就会没有。所以一个dipole 的那种天线的话，它就是要0度、90度的地方，它会接收讯号，接收的最多90度的话接收的没有。手机的话也类似，手机的话它当然不是一个简单的dipole，但是它会把它故意设计成，就比如说它在这个机壳上，就外壳上面有几个线圈的，就是不同的那个通讯的制式的话，它就会有一个不同的圈，因为它频率不一样。就比如说你要上 WiFi 的话，它是2.45G、5G 这样的频率，它就会用一个圈。那如果你要上那个4G、5G 那种频段的话，它就会有另外一圈。甚至如果5G 的话，你要用28 GHz 的那个频段的话，那是另外一个线圈，或者是 GPS 它有一个圈，因为 GPS 的频率大概是1.5 GHz 吧，我没有记错，我有点忘记，反正是1点几 G 的 GPS， 所以每一个不同制式的话，它都有一个自己的线圈，然后它会设计它的那个发射跟接受的方向都是这个往外的。它会尽量让你在讲电话的时候，就是最少的电磁波射到你的身体里面，因为这样一方面的话就是被你吸收了，那对面的吸收就接受不到。另一个的话就是你打太多电磁波进你的身体里面也不好，所以的话它会设计成这个方向的话就是最强的那个电磁波的传输方向。那90度的话，它自然也会是一个比较弱的方向，所以有时候就是你改变一下方向的话，有时候就是接收到接收不到。如果你想要 那个 router 在那边的话，你这样对着它的话，应该会建设的更好。但如果你没有太多遮挡的话，其实可能还好，因为如果室内的话，它有时候反射回来的话，也可以做一些接收，但是反射的话，那个讯号会减弱一点。但是如果是一个小面积的室内的话，没有拐弯太多的话，就还好。可能反射一次的话，那个信号还是可以的。Okay, so next we talk about the potential due to a continuous charge distribution, just like what we do for the E field. If you have continuous charge distribution, we need to separate the charge distribution into many small parts and apply the equation for every small part individually, and then finally add them together. But for the E field, as much as it is a vector field, so we need to decompose it, the dE into different directions. And finally, we try to cancel some of the components and integrate the remaining components. Here, as long as the potential is a scalar field, we don't need to do the decomposition. So we just need to calculate the dV for different parts, and then finally we just add all of them together, and then that's it. So previously we have a V equals K times Q over R, something like this. Okay, so actually here we write it as dV equals K over K dQ over R. K dQ over R. And K should be a constant, so this one will be related to dQ. So in that case, we just put this part in the integral, after the integral sign, and then this K will be put in the front. And we not only need to work on this integration. Okay, so now we examine two continuous charge distribution, a line and a disk. Okay, so for this one, the potential due to a continuous charge distribution, a line of charge. So here we have this line, okay, of length L. We try to compute the potential at point P with a perpendicular distance, orthogonal distance of small d. So in such a way, we try to separate this this line into many small segments. Okay, this one is dx. So for this part, we need to compute the dq or I should say the dv. Okay, so for this part is a dx. So the distance from this dx to p will be r. Okay, but r is not a known variable. The known variable is only d and x. Okay, so actually we have dv equals, this is k times dq over r. Dq over r. And actually we assume that the linear charge density is a constant. So we have dq equals lambda dx, just as what we did before. Okay, so here we have dq equals lambda dx, so we can put this one here. And this one is still the k, and then r in this right angle triangle, r is square root of d squared plus x squared, or x squared plus d squared, according to the Pythagorean theorem. Okay, so we can work on this integration. Okay, so we try to integrate on both sides. Put an integration sign here, put an integration sign here. So it will be v. Okay, so v will be integration of this, and so we have the v equals integration of dv, and then lambda over lambda k. Lambda k will be a constant. Lambda k will be a constant, so we can put this one and this one outside. So the remaining thing is this square root in the denominator. So we have this one to the -1/2 power, -1/2 power, and then we integrate the dx. Then the dx is actually from 0 to L, 0 to L. Yeah, because this one should be 0, this one should be L, this one should be L. So this one will be x. This is 0. This is L. So this one will be x. Okay, so working on this integration, okay, you should have learned it in the calculus class, okay, or you can check it on the appendix for this integration. But just in case you do not know how to integrate this, I can just work it out quickly. So for this type of x squared plus d squared in a square root, so we must assume x to be d times tangent of theta. So in such a way, dx will be d secant square of theta, and then d theta. So in such a way, x squared plus d squared will be d square secant square of theta. Yeah, because 1 plus tangent square will be secant square. Okay, so here we also assume that theta L will be arctangent of L over D. Arctangent of L over D. Why do we assume a variable like this? Because here we just assume that x over d is tangent theta, which means this is theta, this is a right angle, and then this one will be x and then d. Okay, this case is like if we have L, okay, for the full length, and then d, okay, because x is from 0 to L, okay, so we just put L, okay, put L to be the maximum value of x, and then in this case we denote it as a theta L. So this integration I will be integration, okay, of this thing. This thing is x squared plus d squared, and then to the -1/2 power. So which means that this part will go to here, d secant theta. D secant theta. Okay, and then dx will be d secant square of theta, d theta. So which means we can cancel this d and this d, and then this secant square with this secant partially. And then the lower and upper bound will be 0 to theta L. 0 to theta L, because if you put in 0 to here, okay, theta will be 0, and then if you put in L there, okay, it will be this definition. Okay, so what it remains is only the secant theta, d theta, and then from 0 to theta L. Okay, and then to integrate this secant theta, we have a quick trick. Like we multiply secant theta plus tangent theta in both the numerator and denominator. Okay, so it doesn't change anything. Okay, but in this way, d secant theta, tangent square theta d theta will become d tangent theta, and then secant theta tangent theta d theta will become secant theta. Okay, so it will be something like this. So we can write it like this. Okay, something like this. So this is a log of tangent theta plus secant theta, evaluate from 0 to theta L. Okay, so it turns out to be natural log of tangent theta L plus secant theta L over tangent of 0 is 0, secant of 0 is 1, so something like this. Okay, so in such a way, we need to transfer it back to the original variables. So for the tangent theta L is nothing but tangent theta L is nothing but L over D. According to this right angle triangle. Okay, tangent theta L is L over D, and then secant theta L. Okay, this one will be square root of L squared plus D squared. Okay, so according to this, secant theta L will be 1 over cosine. 1 over cosine is actually square root of L squared plus D squared over D. Okay, so we put these two into here. So finally, we have a lateral log of D, and then L plus square root of L squared plus D squared. Something like this. Yeah. So in this case, we can calculate the potential generated by a linear charge line like this. Okay, and then with a distance p. Okay, but this p should be at the end point. Okay, if it is in the middle, the expression will be different. I think it is still doable with head calculation. So if I remember correctly, one of the selected problem is like this. But for other position, the integration is not that good looking. Yeah. Okay, so